If you are asked to make fruit baskets for a party and you are told each basket needs 2 apples and 1 orange, I don't care if there's any leftovers, just follow that recipe. A question we could ask is how many fruit baskets would you make? So 2 apples, 1 orange per basket, we would get 5 baskets, right? And once we run out of something, it's over. We can't make any more baskets. In chemistry terms, whatever we ran out of, in this case, the apples, that's called our limiting reactant or our limiting reagent. I'll be abbreviating that as LR throughout this video. And whatever you had extra of your excess reactant, excess reagent, you can label that with XS, those letters. Be a little chemically clever there. All right, so in this case, we can make 5 fruit baskets. All right, so as we apply this to chemistry, we're going to be looking for these different amounts in the chemical recipe to help us with the math. Notice though, before we get into chemistry, that these coefficients here, the 2 apples, 1 orange, giving us 1 fruit basket, these are counting numbers. They have nothing to deal with weights or masses. We didn't weigh the apples or the oranges. We're counting. So, right off the bat, I want to tell you this, okay? These coefficients right here are counts. Coefficients are counts, okay? Moles are also a counting number, okay? So coefficients are in moles. That's what I'm getting at. Coefficients are not in grams. They are not masses, all right? So that's something I want you to keep in mind. All right, let's get started with today's problem. So the problem today is an acid-base reaction between phosphoric acid and calcium hydroxide. It's a double displacement reaction. And when I have hydroxide as an anion in an acid-base reaction, I prefer to keep the H's from the acid separate from the OH's from the base, and therefore I write HOH instead. Me personally, I find that easier to balance the equation. All right, so here's the question. You have 49.0 grams of phosphoric acid and 50.0 grams of calcium hydroxide. And they're asking us, how much of each of these do we use? And how much of each of these do we create? And we're going to be very comprehensive in this video. We're going to ask and answer every possible question about this reaction. I do realize that for some of your problems, maybe you won't be asked to answer every single thing, but sometimes you will be. So I just want to be on the safe side and be fully comprehensive in this video. I find it easier to teach calculating everything in terms of moles first. So that's how we'll start out. We'll calculate how much of the phosphoric and calcium hydroxide did we use in moles, and then how much of these are created in moles. And then in the second part, we'll do the busy work of using the molar masses from the periodic table to calculate how much stuff we create in grams and how much of this we used in grams. And we can even add one more thought, figuring out how much leftover there is of whatever we had excess of. All right, so that is the question in front of us, calculating stuff. So here's our steps for today. Step 1, we're going to make a balanced equation. Step 2, we're going to do the busy work of changing anything that we have, all of our grams, into moles. All right. Step 3 is our limiting reactant analysis. I'm going to show 2 different ways of doing that. I'm going to have a method where these 2 are done together. Some find that easier, steps 3 and 4. And then I'm going to have a method where steps 3 and 4 are done separately. So I'll show that in a bit. But we're going to do our limiting reactant analysis in step 3 to figure out what our limiting reactant is. And then once we know what that is, in step 4, we'll do our mole-to-mole conversions to calculate everything they asked for in the reaction. How much was a reactant used? How much of a product did we make? All that sort of stuff. Okay? And step 5, if they ask for it, and they do today, we'll do the busy work of using molar masses to convert everything into grams. If you want, you could consider a step 0 where you calculate all those molar masses needed. Just get that over with. Some people like to get it over with. Some people don't mind calculating those molar masses as you go. All right. And these steps I have detailed in our process here. I call this like the conversion train. Okay, we have different train stops. Grams to moles, we're dealing with some substance A. We change substances with the mole to mole ratio from the balanced equation. All right. And then once we have moles of B, we can change those back into B. All right, for steps 2, 3, 4, 5. I outlined those steps here. All right, so let's get started. All right, step 0. Let's do a step 0. Let's get those molar masses over with. All right, what I did is I just looked them up, and then I double checked, but with my own calculations. But I just looked them up. All right. Once you get used to calculating molar masses, sometimes it feels like a chore to just calculate them over and over again. So I went to a reputable source to get these numbers. And to make things simple for the problems here, we'll do everything, we'll use all our molar masses to just 2 decimal places out. I guess for water then, that'd be 18.02. I don't want sig figs to be the major point of this video, even though we will, of course, be following sig fig rules. Okay? All right. So we got our molar masses done. And yeah, that was our step 0. All right, now step 1, we are going to turn this into a balanced equation, a very, very important step. All right, the balanced equation is your chemical recipe. So when I balance an equation, especially for double displacement, I like to look for the most complicated looking thing, the one with the most interesting looking subscripts. Like here we have a 3 versus a 2. And then go from there. Like I say this is the most mathematically complex. Like here we have a 3, but then we only have 1 phosphate. Here we have 2 hydroxides, but only 1 calcium, 1 proton, 1 hydroxide, so 1, 1. This one has a 3 and 2, so I think it's easiest to start with this. So if we end with 3 calciums, we must have started with 3 calciums. If we ended with 2 phosphates, we must have started with 2 phosphates. All right, and 2 times 3 H pluses means we're going to have 6 of these. And hopefully we had 6 hydroxides to go with those H's, and we do. Okay, again, I like to treat this separately from that. All right, good. We have a balanced equation. Step 1 is done. Now, what I like to do is put color and shape codes for each of the coefficients. Okay. What I normally like to do is go in order of black, red, green, blue, just like as if you had one of those like 4-color pens. I feel like that's kind of a fun, easy thing to do. So I'm going to use black circle for that 2 as phosphoric acid, and I'm going to use a red box for calcium hydroxide's coefficient of a 3, and then I'll use a green triangle, kind of a rounded triangle, more like an acorn maybe, for the 6 of water. And then I'll use a blue fluffy cloud Well, we have 1 calcium phosphate, so I'll put a 1 here. Then we'll do blue fluffy cloud for that coefficient. And we'll kind of use these colors as being associated with each of the chemicals so that we just don't get lost in all the text being written out. I feel like the colors makes things easier to observe and organize. All right, so step 1 is done. We've done the balanced equation. Let's get on to calculating moles. All right, step 2, we're going to take all of our grams and turn them into moles. To keep this video simple, I just gave starting amounts in grams for each of our reactants. You may have noticed, I didn't point this out earlier, I also gave a solution volume and concentration. I did the math already, figuring out that would have been 49.0 grams, but at the end of the video, I'm going to walk you through some bonus content. What if instead of grams they only gave you solution amounts? How would you get moles from that instead? I'll have some bonus content at the end. Okay, for now we're not going to focus on those amounts of the solution stuff. We're just going to focus on the 49.0 and the 50.0. Whoops, I don't know why I got crossed out there. That was not the intention. All right, let's get moles. So we'll just have a little checklist going. We need calculations for all 4 things. Or excuse me, just the 2 reactants. The products will come later. All right. So let's start with H3PO4. We were given 49.0 grams of H3PO4, and we're going to convert that into moles. All right, I like to use the train tracks method. Here, I'll show it the other way also. Some people like using conversion factor fractions. They're going to mean the same thing. All right, so let's set up our units. All right, I am in no rush here. The early feedback I've gotten in my videos so far is people like my calm pace of things. So I'll stick with what's working and what you all enjoy. But I know some of you like to speed up my videos, and I do not take offense to that. I am kind of a low and slow guy on purpose. That's kind of how I like to do barbecue and live life, low and slow. All right, so we need a molar mass of phosphoric. We got the 98.00. I always place my units before I put in the numbers. All right, and this will give us moles. Time for the calculator. 49, oops, divided by 98. Oh, wow, exactly a half. All right, so 0.500. Moles of H3PO4. Our units canceled like that. All right, same answer no matter how you write it out. Okay, so got that done. Turn that into moles, and let's squeeze this into the same page. Let's do the same thing for calcium hydroxide. I'm going to use the train tracks method throughout. So our starting amount for calcium hydroxide was 50.0. 74.09. divided by 74.09. 0.675. All right, so there's our two answers for our starting amounts in moles. At this point, I would advise you to not try to make a prediction of what is going to run out. I mean, maybe you'll be able to do it correctly, but I think there's a chance at this point of getting it wrong. Okay, for example, like we started out with 49 grams of phosphoric acid. We started with 50 grams of calcium hydroxide. Okay, just because the calcium hydroxide amount is larger does not automatically mean that this will be excess, the calcium, and then the phosphoric acid will automatically run out first. That might be true, that may not be true. There's a 50-50 chance. Okay, if I had like 5,000 grams, then that maybe be more of a reasonable, higher probability guess. But you know, these substances have different molar masses. That's a 98 for the phosphoric acid. That's a 74. All right, and different weights means how the weights translates to moles will pan out differently. Okay. So then you're like, okay, but I changed everything to moles now, and now I can see that this is definitely less moles compared to that. You're right, it is less moles. Okay. But don't necessarily assume that that's going to automatically mean that the lesser mole will run out. That's all going to depend on the recipe, okay? And whatever's in higher demand, the calcium hydroxide, in this case, has more demand than the phosphoric, 3-2. If it's in higher demand, that means it's going to run out faster, okay? So even though the calcium hydroxide is higher, is it going to be high enough? And that is going to be the basis of our limiting reactant analysis. Okay, that is going to be where we will take these mole-to-mole ratios into account from the coefficients to figure that out. This is going to be the main point of this video. Okay. So, time for our limiting reactant analysis. All right, two methods I will show to figure out how to figure out the limiting reactant. We're going to have a method A, the lowest yield method. In this method, we'll calculate the lowest yield, as it says, and we'll do it for any product. Okay, if they ask you to do like water specifically, you would do it for just water. If they ask you only calcium hydroxide, you wouldn't worry about water, you would just do calcium hydroxide. In this problem, I asked you to do both, so I like to work in the order of the first one listed, which is water, and then we'll do the calcium hydroxide second. Okay. So what we'll do in method A is, this is kind of cool. We're going to figure out what the limiting reactant is, and the theoretical yield for one of the products we chose. Again, I'm choosing water. We're going to figure both of these out in one single step, which is really nice and efficient. Okay, so earlier I talked about the possibility of step 3 and step 4 being done at once with one of limiting a reactant analyses. Method A for the lowest yield method, sorry, I'm going to throw one more acronym out there, we'll do both at the same time, or a lot of it at the same time, step 3 and step 4. Okay. The other method, method B, we'll do only the limiting reactant analysis, and then we'll do step 4 of the calculations separately. And what method B is, this is a have versus need method. How much you have versus how much you need for the reaction. And this will be presented as a table format, a have versus need table. Okay, so again, like I said earlier, it'll take a little bit more time, not that much more time, a little bit more time. But for some people, they'll find this method easier to understand versus the first method. They'll see what the limiting reactant is in hopefully a more obvious way. Okay, so I'll show both, and I'll leave it up to you which one you like better. Me personally, I like method A a little better now. I find it more efficient and easier to do. But I will say maybe the first half of my chemistry career, I had learned method B, and so that's the way I did things. All right, let's start our limiting reactant analysis. We'll start with method A, the lowest yield method. So we will figure out how much water we will make based off of fully reacting all of the phosphoric acid. And then we'll do the same thing with calcium hydroxide. How much water can we make if we react all the calcium hydroxide? We already did the busy work of turning these grams into moles earlier, so we can use that to make life a little faster. All right. All right, so let's start with the phosphoric acid. Okay, and the way I will label this equation is reacting all H3PO4, phosphoric acid, to make H2O. All right, so basically, if we were to write this more as a shorthand, we're going from H3PO4 to H2O. And we're just doing this in moles. No grams for a while. We're just keeping everything simple right now with moles. All right, so let's set up the calculation. We start out with 0.500 moles of phosphoric acid. And we'll want to convert those moles of phosphoric into moles of the water. All right, when you have mole to mole, this is where you use the balanced equation, coefficients. And this is the only time you ever use the balanced equation coefficients. That's going to be in a mole to mole ratio. All right, so go ahead and fish in your notes for that balanced equation. All right, and we have a 2 in the black circle, and then we have a 6 in the green acorn triangle thing. All right, so it's a 3-to-1 ratio. You could simplify it there if you wanted to. It doesn't really matter. You're going to get the same answer. For me, I find it easier to understand just leaving it in the original numbers. So that's actually my recommendation. All right. So 0.5 times 6 divided by 2. Basically, we're multiplying 0.5 times 3, right? Yeah, and that's exactly what we get. 1.50 moles of H2O. All right. And this is kind of a battle. We're going to take this calculation right here. Then I'm going to put a dotted line around. And it's going to battle versus doing the other one, reacting all, what was the other? Calcium hydroxide. To make water. Okay. So same destination of water. And again, I could have gone with calcium phosphate, but I just like to choose the first one. And yeah, so we're doing moles of calcium hydroxide to moles of H2O. All right, so let's find the calcium hydroxide we had. Okay, 0.675. And like I recommend in most of my videos, right, for best learning, I would recommend following along, writing your own notes, doing these calculations the same way I am, so that you get the mental and muscle memory, not just the understanding. And don't just trust what I put in the calculator. Make sure you can get the same amounts. All right. Well, I can't calculate yet if I didn't set it up. All right. So we need to cancel that unit. So that'll become my denominator there. Mosquitoes here in November. Moles of... I'm going to get the mosquito. Hang on. Got it. All right, where was I? Calcium hydroxide to moles of, well, we got water. All right, go to our sheet again. We need a 6 for the water and a 3 in the red box for the calcium hydroxide. All right. So 6 over 3, that's basically just going to be a 2, right? But 0.675. I feel more mentally complete when I type things in as written in my notes. 1.35 moles of H2O. All right, so this is our battle. We have 2 possible amounts of water calculated, but only one can be correct. How can we have 2 different answers? Okay, they have the same units. It feels like we have 2 different possible answers, but that should feel ridiculous, and it is. This is the ridiculous one. It is impossible to make 1.5 moles of water because we have a lower amount that can be calculated. Here's what this calculation at the bottom means. It means that if we react all of our calcium hydroxide, then we would make 1.35 moles of water. What that means is once we've made 1.35 moles of water, we have reacted all of our calcium hydroxide. It is gone. We are down to a 0. So that last little bit of difference between the 1.5 and the 1.35, that's like 0.15. We can't make 0.15 more to get to this other number because, well, we physically ran out of stuff. Okay? This would be like saying in an apples to oranges example that we can make 10 fruit baskets because we have 10 oranges. 1 for each basket, we can make 10. We could if we had enough apples, but we don't, which is why we're stuck at 5. If we got more apples, yeah, but we don't have more apples. So same deal here. We don't have more calcium hydroxide, so this is where it stops. All right, so we did 2 things at once, okay? The first thing, the most important thing, is we figured out what our limiting reactant is. All right, so when I figured that out, I like to make a very, very big deal out of figuring out what my limiting reactant is. Okay, it's not the answer. That's how much stuff we make. It's limiting reactant. Reactant is one of the chemicals we start out with. So I like to circle it and point an arrow at it and go LR. And maybe put an exclamation mark there or something. All right, go crazy. Really make sure that you know where your limiting reactant is because this will be our starting point for all future calculations. This will be our start for all future calculations. The rest of the calculations. Start for all future calcs. And we're going to start with this because since we know this will run out, we know it will give us all the correct numbers in the future. We're not going to ever calculate with this number because it's going to overestimate everything. Okay, and that's garbage. All right, so this is our limiting reactant amount. Now, I talked earlier about how if you use the lowest yield method, you're going to do two things at once, step 3 and step 4, or at least a little bit of step 4. There's still more things to do in step 4, other calculations, but you already got one of them done. We won't have to calculate again the theoretical yield of water because we did it simultaneously. That's pretty cool. Lowest or limiting reagent was determined, limiting reactant, as well as this is our theoretical yield for water. Okay, this is the true one. Not to be confused with the word actual. Actual is what you actually got. This is our true maximum. Theoretical yield just means the theoretical maximum. And this one was false. Okay, this one is garbage. Trash. Basura. Basura. Do you roll that R there? I don't know. I haven't taken Spanish in ages. All right. Gomi. Japanese. Yeah, maybe I should stick with languages I know. All right. What's next? All right. Next step was to show an alternate method of determining your limiting reactant. This is going to be our have versus need method. So we're going to build a table of our reactants. We got the phosphoric acid versus calcium hydroxide. All right, and we're going to have two columns of data. How much we have of each in moles, and then how much we need of each in moles. And by need, I mean how much we need of one to fully react with, use all of the other chemical. And everything will be in moles here. You cannot do this in grams for reasons we mentioned earlier. Okay, so phosphoric versus calcium hydroxide. So in step, man, I'm already forgetting how I number these steps. In step 2, we already did the work of turning things into moles. So we can just reuse those same amounts. 0.5 of the phosphoric. And I know it's not quote-unquote professional to put your units if you already labeled it in the table, but sometimes it helps my psychology. So I don't care. And then we have 0.675 moles of hydroxide. All right, we need to change these into, we need to calculate how much we need. All right, so we're going to calculate how much phosphoric acid we need to fully react the calcium hydroxide we have, and then we'll do the other one, how much calcium hydroxide we need to fully react the phosphoric. So some people, when they look at this table, they kind of have like a diagonal way of looking at things, if that helps. All right, so let's just start with this number, 0.500 moles, and we're talking about phosphoric acid. And basically what makes this method different from method A, really the main difference is instead of calculating a product, we are comparing between the reactants in terms of how we set up our mole ratios. So we'll just convert this to calcium hydroxide. All All right, and then let's set up the other calculation. Let's start with 0.675 moles of calcium hydroxide cancel out the moles of calcium hydroxide, get left with the moles of phosphoric acid. All right, go to the balanced equation, grab those coefficients. I hope I'm not coming down with a cold or something. Boom, boom, boom. All right, so we're just comparing between the reactants. So we have a 2 in a black circle and a 3 in a red box. The 2 in the black circle goes to the phosphoric. And the 3 in the red box goes to the calcium hydroxide. One nice thing about this method is that you use the same coefficients twice. They're just obviously flipped in the other example. All right, let's calculate. .5 times 3 divided by 2. 0.75. Add a 0 for sig figs. And the units that survived was our moles of calcium hydroxide. Which means that goes there, because the units say so. All right. And then this one, 0.675 times 2 divided by 3. 0.45, add a 0 for sig figs, moles of phosphoric acid. All right, and those units means they go there. Okay. All right, we did the calculations. Technically speaking, you actually only have to do one of them, but I encourage you to do both because you get peace of mind of double checking your work. So now that we did the numbers, we can just compare going across if we have enough or not. So we have half a mole of phosphoric, 0.500. We only need 0.450 moles to fully react calcium hydroxide. All right, so this is an excess reagent. Logically, that means calcium hydroxide should be our limiting reactant. But again, we did the other calculation just to check our work. 0.675 moles of calcium hydroxide is what we have, but to fully react with all of the phosphoric acid, we need more than what we have. We need 0.750. Okay, so that means all of our calcium hydroxide will get used up. It's our limiting reactant. And we're going to have some left over of the phosphoric acid. Okay, we're going to have some left over. All right, so at the end of the reaction, we would expect this solution to have a pH lower than 7, acidic conditions, if we use like pH meter or pH paper or something. Okay. Did we get the same result as method A? Let's check the work on that. So method A was the lowest yield method. And, whoops, this is the wrong paper. There it is. So in our method A lowest yield method, we also got calcium hydroxide to be our limiting reactant. Okay, same number, same result. Okay. If you like method B better, definitely feel free to use it. What I like to do at this point is I circled what my limiting reactant is, and then all the other numbers are likely not going to be necessary for any future calculations. So I like to get rid of them, cross them out, so that I know to choose the correct number. Now we can go to step 4, or finish step 4, which is to calculate everything for how much is getting used for the reactants and how much stuff we make for the products. Okay. Again, if you did method A, you have already done one of your step 4 calculations. We only did the theoretical yield for water, but we haven't done it yet for calcium hydroxide. Okay. So now with either method, we know calcium hydroxide is going to be our starting point for all calculations. All right, so we'll start with this. Okay, limiting reactant, this is our starting point for everything. And we'll calculate how much water we'll make. We did that already in the lowest yield method. We will also calculate how much calcium phosphate we'll make. And we can even calculate how much calcium phosphate we make. And we can also calculate how much phosphoric acid we use, as well as how much leftover there will be. All right, very powerful being able to calculate all these things with our limiting reactant as the starting point. Let's get started with that. So I'm going to label this paper step 4. Make sure I'm on the screen. And these will be our calculations. All right, no fancy acronym this time. So let's kind of recap things. We have already done moles of calcium hydroxide to moles of water, and water was a product. Okay, we haven't done moles of calcium hydroxide into moles of calcium phosphate, also a product. And we still haven't done moles of calcium hydroxide into moles of phosphoric acid reactant used. Okay, so notice the language is a little bit different. We have products being made versus reactants being used, but you're going to notice the math is exactly the same. You're going to just use that mole ratio for everything from the coefficients. Same process. Okay, just mole ratios for everything. Okay, so we did that one. Let's do the next one. Yeah, I'm definitely coming down with something. Maybe y'all can hear it in my voice. All right, so we're going to do this middle one, hydroxide to phosphate, calciums. Okay, so we start with the limiting reactant for everything. Okay, so basically, when you're in doubt, you're in life and in these stoichiometry problems, when in doubt, bounce the equation, get everything to moles, use limiting reactant for everything. And then we wanted calcium phosphate. Okay, let's grab the coefficients. So 1 in the blue fluffy cloud, and then the 3 in the red box. One. Okay, so basically in our calculator, we divide by 3. Some of you may be feeling that perhaps the video is a little slower than it needs to be because these calculations can be done pretty quick. And yeah, I agree with you actually. It's just that I want to make sure that you all see the proper way of writing your units, especially if there's so many different substances going around. I realize for some of you, you may be like, well, if it's a multiple choice question, I may not feel like showing the work. I get that. I can't get you to change your mind there. But I just like to take my time and have you all see where everything is coming from. So that's kind of my 2 cents there. All right, so those units survived. We did the conversion. And I think I can fit this in the same page, so we did that. Okay, I'm going to have to write a little bit smaller. But, okay, it looks good on the camera. I think we'll be okay. So start with the limiting reactant again. Set up our units to cancel. Set up our units to survive. H3PO4. Canceling out units to me is like almost just as satisfying as a good slice of pizza. Preferably thin and foldable, like New York style. All right, we got 2 there. The black circle. And then, oh yeah, 3 with the red box. It's always going to be a 3 in the red box for the remainder of this problem. In our denominator. Okay, so basically we're just taking that number and multiplying by 2/3. Am I on the screen? There we go. 0.450. Moles of phosphoric acid. Used. All right, good. And we can do even one more calculation, kind of a bonus calculation. May not be a bonus depending on your instructor, but we can calculate how many moles of H3PO4 unused left over. All right, let's see. I'll try to fit it into this top right corner here. All right, and to do that, this is going to be actually a subtraction problem. So let's look for how many moles of phosphoric we had to start, and we're just going to subtract. All right, that was way back in step 2. We had 0.5 moles of phosphoric to start out with. And we're going to subtract the amount that actually got used. Or technically speaking, the theoretical maximum that could be used, the 0.450. All right, and we get 0.050 moles H3PO4 left over. Okay, proving even more that phosphoric acid was not our limiting reactant, but it was our excess reagent. All right, so we have, if all they asked for in whatever you're doing with moles, we would be done at this point. To state the obvious, but sometimes the obvious is not obvious to us. We would have 0 mole left over for the calcium hydroxide because we already figured out it's going to run out first. Okay, that's not a calculation that you have to do because you can just think your way through that one. Okay. All right, let's do, I suspect most of you will want this, unless you're really comfortable with molar masses. Let's just take all the mole answers we have, and let's now just do the busy work of converting those amounts into grams, and we're going to be using the molar masses that we got early in the video. So step five. I hope I can get this video under an hour. We'll see though. I have revised so many drafts of this video, trying to get on a short side because I knew how long it'd be. Step 5, we're going to do moles to grams. Okay. I really like to call this busy work. Not to like insult it, maybe just a little bit, but it's just molar masses. It doesn't involve the crucial mathematics of the mole ratios from the balanced equations. Okay, this is just basically the unit cosmetics of whatever is needed or being asked for. Okay, so I think we can do all these on one page. I think that would be more efficient. So I think I'm just going to set them up, boom, 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 and calculate away. Race ya. All right, got our calculations labeled and set up. Phosphoric acid, moles to grams, calcium hydroxide, moles to grams. We'll keep our reactants on the left side of the screen. And then we'll do our products here. Water, moles to grams, calcium phosphate, moles to grams. Okay. And I have a deliberate reason, you'll see in a moment, of why I'm doing reactants one side, products the other side. Not just for organization, but it's going to show us something about the reaction. Okay, but let's first do the calculation. All right, so here we go. All right. I think you're winning the race already. I'm going to blame the cold or whatever the heck I have. Water. Probably winning the race at this point. I am in a blank. I can't cheat with the pause button. I can't cheat. All right, let me see. Oh, man, I did the totally wrong thing. All right, there we go. You win. You probably beat me. I'm sick. Don't worry if you didn't, though. I've been doing chemistry for a long time. All right. So that molar mass, that molar mass, that molar mass, that molar mass. Put them in. Calculate. All right. So here's the numbers I get. I get 44.01 grams phosphoric acid, 50.0 grams calcium hydroxide, to finish out our reactant side. 24.3 grams water, 69.8 grams calcium phosphate for our product side. So this is one of the things I wanted to talk about in closing the video. Okay, even if they don't ask for the grams, I think there's something powerful about calculating the masses about both the masses for both sides, which is you can check your work using the law of conservation of mass. That is to say, in chemistry, we don't create or destroy matter because chemistry is simply the subject where you just rearrange atoms. You're just rearranging bonding parts. So our reactant masses and our product masses should add up to the same exact thing. Let's confirm this together. All right, so checking our work. (94.1) grams of reactants. So hopefully we get the same number, or at least really close to it on the other side. Sometimes there's a little bit of rounding error. 94.1 grams of products. Let's see if that's the same number. It is. Okay, great. All right, you can't create or destroy matter unless you're in a nuclear reactor, all right, or like in a star or something. So that's a way of checking our work. Okay, so this video is almost done. For some of you, it might be done, but for others, I promised how to work with a scenario where you need to get moles from not a mass. Let's say they didn't give you that mass and instead they gave you some solution data. How would you get the moles from that? So let me show you that. All right, here's our little bit of bonus content. How do you get moles from solution information? What we've worked with so far is turning masses into moles using molar masses we get from the periodic table. Okay, but if you're given something like milliliters, this is how we would get that into moles. Okay, milliliters first, we would have to change that into liters just using metric conversion. Okay, 1,000 milliliters and 1 liter. Once you have something in liters, you can use molarity. Okay, capital M meaning molarity. And molarity, whereas a molar mass is grams per mole, or moles per gram if you flip it. If you have the flip version of molar mass, grams times moles over grams cancels your grams, leaving you with just moles, and you're there, right? Well, molarity is units of moles per liter. So once you've done the busy work of changing your milliliters into liters, you can multiply your volume by the molarity, cancel out your liters, and that's how you get to moles. And once you have the moles, you can do the rest of the stoichiometry problem like we showed, like normal. Okay. While we're out here having your attention, I mean, you're watching bonus content already. So what if, like you could go this route for solutions. Okay. Going that way. This would just be like a mass, right? But what if you're given a volume, but not for a solution, but for like a pure substance, okay? Then if it was a pure substance, they probably wouldn't give you the molarity then, okay? There'd be another route. This would be using the density. Okay, density is grams over milliliters. So let's say they gave you like gasoline, octane or something. And they gave you some amount of fluid for that. In milliliters, it's pure octane. If you had the density of octane, you can cancel the milliliters, and then you just be at the grams there, and then you can use the molar mass of whatever it is. All right. Basically, what I'm getting at, folks, is there's more than one way to get at moles, and sometimes a little bit of creativity will be called for. For 101 students, I don't really do the density stuff so much. I kind of limit it here and there. But there's one more route, and this one is expected. What if you have a gas? Okay. I haven't made a gas video yet at the time of this filming, but just to preview that in case you've studied a little bit about gases already, there's the so-called ideal gas law. PV equals nRT. P stands for pressure, V stands for volume, N stands for moles, T stands for temperature in kelvins. All right. And then we have this constant R. Okay, that's not a variable. That's just the ideal gas constant. But we can rearrange this algebra to get N equals PV over RT. And so there's the gas constant. If you know the pressure of the gas, the volume of the gas, and the temperature of the gas, and it's a pure material, rather than weighing something or measuring a volume, you can just use these three environmental variables and the gas constant to figure out how many moles of gas you have. And that's another route to getting moles if you had like a gas stoichiometry problem, for example. All right, but there's a lot of ways to get to moles. Well, I don't know if that was a lot, but I showed like 3 or 4 ways here. All right. I think I'll call it a wrap on this video. All right, I thought about putting maybe a % yield final example, but I think this video has gone on long enough, and you can consult that in my previous stoichiometry video on how to calculate a % yield. Okay, all the yields here were theoretical yields today. Actual yields that you use in a % yield calculation is not something you can calculate. It can only be measured. All right. Hopefully this helps. Thanks for your attention and time, and let me know if you have any questions or suggestions out there. Thanks. Take care.